Good morning. I'm very happy to interact with you all, researchers and faculty members, through the faculty development program organized by Jamal Mohamed College. I am Dr. Ismail Mohideen, Principal, Associate Professor, and Head of the Department of Mathematics, Jamal Mohamed College. Today, I'm going to discuss about network optimization problem. Now, first of all, we should know what is a network. Network is a graph consisting of a finite non-empty set of vertices and a set of edges connecting all the vertices and a set of associated weights of edges. If you ignore the weight of the edges, it is just a graph. So graph becomes network only when we add weight, or we can simply say that weighted graph is a network. Okay, now what is a network optimization problem? Network optimization problem is the problem of determining the optimum solution of a network with respect to the given optimization criteria. Many real life problems we are facing in day-to-day life can be formulated as a network optimization problem. For example, transportation network, communication networks, flow distribution network, neural network, planning networks. These are all some of the networks model. So in all these network model, the primary aim is to optimize the performance with respect to predefined objectives. Now, what are the objectives? What are our goals? So it will vary from model to model. In a transportation network, the objective we may consider of finding shortest path from a source node to a specified destination. In a communication network, the objective may be to minimize the delay of information transmission. Similarly, in a flow distribution network, the objective may be to minimize the time of flow. And in neural network, the objective may be to minimize the errors or deviation. Similarly, the objective in the planning networks may be to minimize the costs. So here in today's discussion, I am going to concentrate only on shortest path in a network. What is a shortest path problem? So shortest path problem is a problem of finding a path between two vertices, or in a graphical sense, it is a node of a network such that the sum of the weight of its constituent edges is minimized. So the objective involved in such networks may be minimization of cost or time or risk and maximization of comfort, stability or reliability. So the objective is defined by the decision maker. In a graph theoretical concept, the shortest path means the number of continuous edges connecting the source node and destination node. But here, the shortest in the network model, it is not necessarily it is a path or it is a distance. We are in the place of a shortest path. We can consider is minimization of cost or maximization of comfort, stability, etc. What are the different classes of shortest path problem? For example, one pair problem, single destination problem, single source problem, shortest paths passing through specified intermediate nodes, and all pair problem. So these are all different classes of shortest path problem. Now, what is a one pair problem? Suppose we want to find a minimum or shortest path between two pair of nodes alone is called one pair problem. Suppose one want to move from a city to another city, He need not want the entire shortest route from all the nodes. He want to travel from a particular A to another city B means it is a one pair problem. Then the single destination problem. Single destination is one, source is the nodes of all the network can be source. Suppose here is a conference in Jamal Mohamed College in Tamilnadu, Tiruchirappalli. So all over India, people may wish to come to Jamal Mohamed College. So everybody wants to know the shortest path between their place to Jamal Mohamed College. So such problem is called single destination problem. And another, if you revert this, it will be single source problem. Suppose after the conference is over, everybody want to leave Jamal Mohamed College to their own places. So such problem is called single source problem because everybody wants to move to their own places from Jamal Mohamed College after the conference is over. This is called a single source problem. You can consider this as a broadcasting problem also is considered as a single source problem. Similarly, shortest path passing through specified intermediate node. What it means? Suppose I want to move from a city, for example, from Chennai to Delhi via from Chennai to Delhi via a particular place, for example, Hyderabad or some place, Mumbai, etc. So this is called the shortest path passing. I want to find the shortest path from this place or particular city A to C passing through the city B. This is called the shortest path problem passing through specified intermediate nodes. It may be one or more intermediate nodes. Similarly, all pair problem, the road map problem is a very good example for all pair problem. That is, from every city to every other city, we want to find the shortest path. So such problems are called all pair problem. Now, what are the different type of shortest path problem? Already we have discussed the objectives. So depending on the objective, the problem is said to be single objective shortest path problem or multiple objective shortest path problem. So if you consider the your objective as only one, you want to travel from a place to other considering only the distance, then it is called a single objective shortest path problem. But in realistic sense, it will not work. We require, suppose I want to travel from a city to another city, I want to minimize the time, I want to minimize the cost even. Similarly, I want to travel in a sophisticated way. So all these objectives will be considered. So the decision maker can decide the number of objectives. If the number of objective is more than one, it is called multiple objective shortest path problem. Now, this is an example of a single objective shortest path problem. Suppose I am considering 6 cities and the arc edges are specified that is linking the cities, and also the numbers inside the circle denotes the city names, and the number between the cities and or the number mentioned above the arc or edge is called weight of the that edge, or you can say that it is a distance between 1 and 2 is 4, between 2 and 5 is 2. Suppose I am a layman, I want to find the shortest path. What I will do is I will consider the paths separately, individual path. What are the different paths connecting 1 and 6? Suppose I want to consider there is a one pair problem, there is one to one problem. I want to travel from city 1 to city 6 with minimum distance. Then the layman approach will be exhaustively that is determining all the paths, and then the weight of the path will be calculated. So if you consider in this problem 1 2 5 6 is a path, 1 2 3 5 6 is a path. Similarly, all the paths have been determined first. Then the value of the path means the total length. Length here means summation of weight constituting that path is considered. It's very simple. We can find the minimum of all these values. So 11 is the minimum weight. Therefore, the shortest path is 1 to 2, 2 to 5, 5 to 6 is the shortest path. But is it always possible to find the shortest path? Definitely not, because it is only 6 node network. Determining all the paths between 1 to 6 itself is very difficult, because here there are 7 paths. But if it is a completely connected network, or we can say complete network, complete graph, we can say, that means between every pair of vertices there is an edge. What I mean here is 1 to 2 is an edge, means 2 to 1 is also, it will be connected. That is, similarly 2 to 5 is an edge, 5 to 2 is also an edge, that weight also given. You imagine how many paths will be there. So it is very difficult to identify all the paths exhaustively and then determine the value of the path and then determine the minimum value is very difficult. So we require some algorithm. So using that algorithm, using software, we can find out. So what are the different type of algorithms? There are many algorithms available to find shortest path. Here I am mentioning only some of the algorithms. There is one is called Bellman, and here I am mentioning that no restriction on sign. What it means? That is, in a network, for example, in the previous network, 1 to 2, 4, it, all the weights are positive. Suppose negative weights. One may ask, sir, how the distance is negative? We are not only considering the distance, it may be cost. You can consider the weight as that is income or profit or loss. So negative weight also is possible in the real life situation. Therefore, here the Bellman have given an algorithm in 1958 itself, and but he considered the all the weights of the edges should have a positive or a zero weight. And order of this algorithm is order of n power 3. I will explain about the order and the complexity in the next slide. Okay. Then Dijistra's have given an algorithm. Here also the negative arc weight, no negative arc weight, negative arc weight is not allowed. The algorithm require order of n square. That is computational complexity of the algorithm is order of n square. Similarly, another algorithm is developed in 1962. Here also, negative cycle is not allowed. Negative weight is allowed, but negative cycle is not allowed. So you one should understand what is a negative cycle. If you consider this algorithm, here in this algorithm, there is a path, there is a edge between 2 to 5. If suppose the edge is reverted, for example, instead of 3 to 5, if it is 5 to 3, and instead of 2 to 3, it is 3 to 2, then there is a cycle. And if I put weight for this as minus 3 and this as minus 2, the sum of the cycle, the sum of the edges constituting the cycle will be minus 1. So such cycle is called negative cycle. So Floyd and Warshall in 1962, he developed an algorithm. He accepted or he included he is considering the negative weight also, but it should not contain negative cycle. If it contains a negative cycle, Floyd and Warshall algorithm will not work. And the another gentleman in 1970, N, he developed an algorithm. Its time complexity is order of n power 3 without any restriction. No restriction on sign. That means it may be positive or negative, or even it can have negative cycle also. In even with network with negative cycle, the N's algorithm will give the answer. And if it contains a negative cycle, after n minus 1 iterations, it will say that the algorithm has a negative cycle. But if it contains a negative cycle, all the algorithms will not give the shortest path, but it will indicate that the network is having negative cycle. Now one should know what is the order. Why it is required? Because every time suppose there are here you can see the algorithms are developed in 1958, 59, 62, and 70, and between these years, many algorithms have been developed. Now the question is whether my algorithm is better than the existing algorithm or not. Because here many researchers are here. You may develop an algorithm and you want to check whether my algorithm is better than the previous algorithm. Or suppose you have written a paper and submitting the paper to some journals. The editor of the journal may ask why I have to accept this algorithm. In what way your algorithm is better than the existing algorithm? So the question may arise. So at that time, you have to specify that your algorithm, that is, you have to prove the algorithm. What is the proof? The proof is in finite number of steps, the algorithm will give the answer. That proof you should give, number one. And number two, the algorithm always, it is very important, always will give the minimum, that is optimum solution. And another very important thing is the time complexity or computational complexity of the algorithm. So what the computational complexity means? Analyzing an algorithm determines the amount of time that the algorithm takes to execute on a particular input size. Here, the time is not our regular hour, minute, that time. It is the approximate number of operations that an algorithm performs. So, this time is different from the regular time that we are using. So here it is the number of operations. What number of operations? Is it possible to calculate each and every operations in an algorithm? Definitely not possible. So usually the mathematicians used to consider only comparisons and arithmetic operations as the elementary operations. So all other will taken care of. Then what about the input size? If suppose I am considering the network or graph, the number of nodes is the input size. In the example already we considered the number of nodes is 6. So here input size is 6. So in an n node network, the input size we will consider as n. There are different types of analysis. So three different types of analysis. What are those three types of analysis? One is best case analysis. What do you mean by best case analysis? That means the best case running time of an algorithm is the input that requires the algorithm to take the shortest time. So I can explain this with an example. Suppose you want to, it is a sorting, you want to find a number, whether the number is available, searching algorithm, whether the number is available in the list of given numbers. Okay. So my problem is finding whether a number is available in the list or not. Suppose you are given 100 numbers, and what the best case indicate is if the searching number itself is in the first instant, the first number itself is in the given set of numbers, the first number is the number that you are searching, means immediately in a fraction of second your algorithm will say that yes, the number is available. This is the best case analysis. If suppose I am considering average case, it is very difficult, so I am not going to discuss those things. The worst case analysis. What is worst case analysis? If suppose you are, I am considering the same the problem, that is problem of finding whether a number is available in the given list of numbers or not. If suppose your number is not a first number, so you will consider the second number, whether the number I am searching is a second number or not. It is also not correct. Then third, fourth, fifth, and you are considering all the numbers. Finally, you are coming to the conclusion that yes, the number is not available in the list. So this is the worst case. So no other problem will take such an enormous number of operations to check whether the number is available or not. This is called worst case. Here in all the algorithm, we are considering worst case analysis. So the already you have seen order of n power 3, order of n square, order of n power 3. These are all the worst case analysis. Okay, now we can consider what do you mean by polynomial time algorithm and exponential time algorithm? Suppose, as I already told, suppose you have developed an algorithm and you have proved that it will complete in finite number of steps, and you also proved that the algorithm works well, and also you are finding the time or computational complexity. If your computational complexity is order of n power k or order of n, okay, well and good, because where what is n? N is the number of nodes we have already told, and what is k? K is a small number compared to n, very small number, or a small integer, or you can say it's a number comparing to n, it is less than n, it should be less than n. So this is called a polynomial time algorithm. And another algorithm is called exponential time algorithm. What is that exponential algorithm? Order of n power n, or order of n factorial, or order of 2 to the power n, or order of 3 power n. Such algorithms are called exponential time algorithm. What it means? The distinction between polynomial time algorithm and exponential time algorithm has a particular significance when considering the solution of large problem instance. This is very important. The solution of large problem instances. Gary and Johnson illustrate the differences in growth rates among several typical complexity functions of each type, where the functions express the execution time in terms of microsecond, and which are reproduced here. Yes, my dear gentlemen, you can think, or we are having our smartphone, our computers, and supercomputers. And what we are doing, we are solving many problems using computers. In fraction of second, we are getting answers. So we are thinking that it is possible for computer to solve all the problems in fraction of second. Just you see this table, the time complexity function. Here the n means number of nodes you can consider. N is the number of node. Here I am considering 10 node problem, 20 node, 30, 40, 50 and 60 node problem. For example, this is given by Johnson's and Gray. And time complexity I am giving n, n square, n power 3, even n power 5 is a polynomial time algorithm. And the last two rows indicates 2 power n and 3 power n. It is exponential algorithm. Now, just think, if you can think of 20 node network, even 20 node network. If the time complexity is the order of n, in point not 2 microseconds, we will get the answer. Such is happening in our day-to-day life. We will feed some problem, we will try to solve in a microsecond or in a nanosecond, we will get the answer. If it is n square, you just compare, it required point not 4 second. If it is n power 5, 3.2 second. These are all polynomial. If it is exponential, if it is 3 power n, that is order of 3 power n, n is the number of nodes. In even 20 node network, 20 node is a very minimum number of nodes. In a practical situation, we may have 50 or 100 or 1000 nodes. But here, even with the 20 nodes, if the algorithm that you have developed is of 3 order 3 power n, you require 58 minutes. That is approximately 1 hour you have to wait to get the answer. Okay. Anyhow, we will get the answer in 1 hour, no problem, if 20 node network. But if it is a 60 node network, just 60 nodes, okay, now order of n required 0.406 second, order of n square required 0.0036 second, no problem. Order of n power 3 means 0.2167 seconds, and if it is order of n power 5, you require 13 minutes, no problem, sir. But if the computational complexity is exponential, that is order of 2 power n or order of 3 power n, you have to wait, you have to feed the problem, after inputting the problem, you have to wait for 366 centuries to get the answer. So suppose we are developing an algorithm and the time complexity is exponential, no one will accept our algorithm because while solving a large problem it required 366 centuries. So we will not consider such algorithms as algorithm even, because no other way, because it is not possible to get the solution. Okay, but in some cases we will accept the exponential algorithm also, because if there is no algorithm or polynomial time algorithm available to solve simple problems, for example 20 node problem or 10 node problem, we can apply those algorithms to get the solution. Okay, so this is regarding the time complexity. So if you develop any algorithm, one should compulsorily know the computational complexity of the algorithm. Now we will discuss. I didn't discuss any algorithm for solving single objective. There are plenty of algorithms available in the literature. One can visit and one can solve single objective very easily. Now multiple objective shortest path problem, MOSPP. What it means? Objective shortest path problem means in a network, if the number of objectives is more than one. I already discussed in the beginning. In a multi-objective shortest path problem, the objectives may be my objective. For example, I want to travel from a city to another city. I may think of with the minimum time I have to travel. I want to travel with minimum time. I want to travel with the minimum cost. I want to travel with the maximum sophistication without any risk, reliability. All these things will constitute my objective. If the number of, if you can consider the terminology, a network represented by n is equal to v comma e. We always know v is a set of all vertices, e is the set of all edges, and d is defined as a function from edge to r power m, that is m tuple. That is, every edge will associate a vector weight dij1, ij2, etc. dijm. Here m represents the number of objectives. So if m is equal to 1, it is a single objective network optimization problem. If m is greater than 1, it is called multiple objective shortest path problem or network optimization problem. Now, what is the value of the path in a multi-objective case? Single objective case we already discussed. You can see the definition. And in a multi-objective case, we should know the order relation also. Suppose you want to find a path, weight of a path, then the component-wise addition should be made. That we can see with an example afterwards. Okay. Now, what is our order relation? You already many of you may be knowing about the order relation on R power m. Let A is equal to an m tuple and B is another m tuple. B two vector elements of R power m. A less than, in terms of order relation, less than B means, that is A less than B if and only if AI, that means ith component of A should be less than or equal to the corresponding ith component of the other vector Bi for all I is equal to 1 to m. Condition number 1. And condition number 2 is Ai is strictly less than Bi for at least one I. Then only we can say that A less than R power m of B. Then only we can say that A in the sense of minimization, A dominates B. If it is maximization sense, B dominates A. Okay. Now, what do you mean by non-dominated solution or Pareto minimum solution? This is very important to to understand the multi-objective optimization. So this terminology is very important. That is why I will explain with an example. A point x star belongs to capital X, it is a subset of R power m. That means it is a m tuple is a Pareto minimum. It is a name of the name of the author is Pareto. That is why it is called a Pareto minimum. You can always say that non-dominated solution of the set of vectors capital X if there does not exist any other x. You understand this? This is very important. X1, X2, etc. Xm belongs to X such that X less than order relation X star. That is, if we do not able to find an X such that X less than X star, then X star is said to be Pareto minimum. I can take a bi-objective vectors. Now I am considering four bi-objective values or vectors 4 comma 5, 5 comma 4, 6 comma 2, 5 comma 3. If suppose you are given 2 comma 3 comma 5 comma 6 and find the minimum, you can easily say that 2 is the minimum. Comparing all other values, simply we can say. But how can I compare 4 comma 5 and 5 comma 4? Comparing 4 comma 5 and 5 comma 4 and you please tell me that which is minimum. Definitely it is not possible, because if you compare the first component of both the vectors, 4 is less than 5 but 5 is greater than 4. Comparing these two vectors, vector number 1 and vector number 2, so we can say that 4 comma 5 and 5 comma 4 are not dominating. 4 comma 5 is not less than 5 comma 4 and also 5 comma 4 is not less than 4 comma 5. So 5 comma 4 is not dominated by 4 comma 5 or 4 comma 5 is not dominated by 5 comma 4. Now I am considering first and third, where second is not non-dominated between these two. Now I am considering 6 comma 2. 4 is less than 6 but 5 is greater than the corresponding second component 2. Therefore, this is also non-dominating. Now I am comparing 4 and 5 comma 3. 4 is less than 5, 5 is greater than 3. So 4 comma 5 in the set of 4 vectors, 4 comma y is not dominated by any of the vectors. Therefore, I can include 4 comma 5 in the set of Pareto minimum vector. I think you will understand in the next example. 5 comma 4 I am considering again. First vector I have selected in Pareto minimum. The second vector 5 comma 4 is already have been compared with 4 comma 5. Now I am comparing with the third vector 6 comma 2. 5 is less than 6 but 4 is greater than 2. So both are non-dominating. Now I am comparing 5 comma 4 and 5 comma 3. 5 is equal to 5. Okay, good. 4 is greater than 3. That means in the sense of minimization, 5 comma 4 is dominated by 5 comma 3. Therefore, I will exclude 5 comma 4 from the set of Pareto minimum vector, because there exists a vector 5 comma 3 which dominates 5 comma 4. Therefore, I include 5 comma 3 in the set of Pareto minimum vector. Now coming to 6 comma 2 and 5 comma 3, because you need not compare 6 comma 2 with 5 comma 4, because non-dominated vector has been already selected. Now 6 comma 2 is compared with 5 comma 3. 6 is greater than 5, 2 is less than 3. Therefore, I cannot exclude 6 comma 2. I have to include 6 comma 2 in the set of Pareto minimum vector. Therefore, among the four values or vectors, the set of Pareto minimum vector or non-dominated vectors are 4 comma 5, 6 comma 2 and 5 comma 3. I think with this example you can understand what is non-dominated solution of a set of vectors. Now non-dominated path or Pareto minimum path, you can better understand the path, because a path which is having non-dominated vector is called a non-dominated path or Pareto minimum path, that you can easily understand. Now non-dominated vectors. With the example you can understand. Anyhow, this is a definition. Two vectors. You are considering A is a vector of M tuple, B is another vector M tuple vector, are said to be non-dominated if none of the following order relation is satisfied. It is very important. none of the following order relation is satisfied. What are those order relation? Three. We all know in the law of trichotomy, A less than B, or A will be greater than B, or A is equal to B. These are the law of trichotomy. Here also, A is less than B, component wise, or in terms of order relation. Or B is less than A. We cannot say that A less than B implies A not less than B implies B is greater than A. That cannot be always in a non-dominated set. It is not possible to tell like that. So we have to check whether A in order relation A less than B. If not, check whether B is less than A. If that is also not B is not less than A, then check whether A is equal to B. So in the set of non-dominated vectors, all these three will not be satisfied. Now comparison of two vectors. How can we compare two vectors? A and B are two vectors. Only one of the following is true. So here it is not law of trichotomy. Only one of the one of the following is true. Either A dominates B, or B dominates A, or A equal to B, or A and B are non-dominated. So there are four categories. This is comparison of two vectors. Negative cycle I have already explained. So I explained in a single objective case. In a multi-objective case, if at least one component of the weight of the cycle is negative, then it is called negative cycle of a network. If a network is containing at least one negative cycle, the network is said to be a network with negative cycle. Now there are many algorithms, recently developed algorithm, and the modified algorithm. I am not going to explain all those things. Modified algorithm to compute Pareto optimal vectors. What is that Pareto optimal vectors? I have explained. Recently, I have explained all the things, how to find non-dominated vectors. But through computers, by developing software, how to find Pareto minimum vectors, Dr. Sastry, Ismail, Mohideen have developed an algorithm during 1999, and in order of R square, where R is the number of vectors. If there are R vectors in order of R square time complexity, we can find the set of non-dominated vectors. So order of R square means that is if it is a number of that is the time complexity is polynomial time complexity, so we can always accept. It has been published in JOTA. And this is an example for multi-objective shortest path problem. I am considering the same network with multiple objectives. Okay, now first I am going to explain it with a layman approach, that is exhaustively finding, writing all the paths and finding the value of the path. Value of the path, as I already explained, we have to add component wise. First component of first edge and first component of second edge, first component of third edge. If you add in the first case, for example, 4 plus 2 plus 5, it is 11. Similarly, 2 plus 5, 7 plus 1, 8. So value of the path 1, 2, 5, 6 is 11, 8. Similarly, in the case of second path, it is 16, 9, and in the third case, 14, 12, etc. Now, my aim is to find the Pareto minimum path, or the set of Pareto minimum path, because in a realistic situation you can always find a single optimum solution. It is very important while studying multiple objective optimization problem. It is very important that you can always find single optimum solution in a single objective network optimization problem, but it is not the case in multiple objective case. In multiple objective case, normally we won't get single optimum solution, rather we will get only multiple, or we can say non-dominated solution. At least we will get two solution. In a rare case, usually in a realistic case, we won't find a single optimum solution in a multiple objective optimization problem. You consider this case. Here there are one, three, yes, seven paths are available, and If for the 7 paths we have seven vectors, 7 values of the path. Now we want to find the non-dominated values. As I already discussed, and using the previous algorithm, we can find the non-dominated values. Here the non-dominated values are 11, 8, 14, 3, 12, 6 are the non-dominated values, because why 11, 8 is selected? 11, 8 is will not be dominated by any of the three values 11 comma 8 14 comma 3 12 comma 6. Rather I can tell like this: why 16 comma 9 is not included in the non-dominated set of values? Why 16 comma 9? You consider the first vector. The first component is 11 is less than 16, and 8 is less than 7, sorry, less than 9. Therefore 11 comma 8 dominates 16 comma 9. Therefore 16 comma 9 is excluded from the set of non-dominated values. Similarly, 14, 12 is also dominated by 11, 8, so excluded. 19, 16 is also dominated by 11, 8, that also have been excluded. Then 17, 10 is also excluded, because all these non-dominated values dominate 17, 10. Therefore, ultimately, we got 11, 8, 14, 3, 12, 6 are non-dominated values. What it means, it is very important. In the single objective case, we got 1, 2, 5, 6 is the optimum path or minimum path or shortest path. But in the case of bi-objective, even bi-objective case, we got 3 paths. One is 1, 5, 1, 2, 5, 6 is one path. 1, 3, 5, 6 is another path. And 1, 3, 4, 6 is another path. There are 3 paths. Now, how can I conclude? So this is how the multiple objective function is very important. If suppose I am considering the first component as hours to travel, and the second component is the that is cost. For example, 11 hours and 8 rupee. Another one is 14 hours and only 3 rupees. Another one is 12 hours and 6 rupees. So the decision maker can select the non-dominated solution. So here all the three are solutions, all the three are non-dominated, or we can say all the three are Pareto minimum solution. The decision maker can select which suit the decision maker. And another important point, in single objective case, you cannot find all the path as optimum path. But in the multiple objective optimization problem, it may occur that all the paths are non-dominated path. All the 7 paths may be non-dominated. So that is a very big problem in multi-objective shortest path problem. That is why we always if you try to find the non-dominated path or non-dominated values of a multi-objective network, we always end up with exponential time algorithm. Now, there are many algorithms available in the literature, and one such algorithm have been developed in 1980 and by Hansen, and in 1984 Martins, and our Carley and Moon, the famous mathematicians, they developed an algorithm in 1985. See, the order or time complexity or computational complexity is order of mn power 2n minus 3 plus mn power n. What it indicates? M is the number of objective, n is the number of nodes. Just think of the Johnson and Gary's comparison. So definitely, even for 16 node network, it will take more than 300 centuries. So for problem with the minimum number of nodes, 10 or 6 nodes, or even 10 nodes, or even or 20 nodes we can solve, or otherwise it is very difficult to solve such problems. Now, my dear audience or researchers and faculty, young faculty members, you can do research in this topic. Try to find the polynomial time algorithm to solve multi-objective shortest path problem. And we have also developed some of the algorithms. For example, Dijkstra's algorithm is available, and we modified the Dijkstra's algorithm into multi-objective case. That is called generalization of modified Dijkstra's algorithm. And another algorithm we developed, generalization of modified N's algorithm. And then, combining these two algorithms, we have developed another new algorithm. But all these algorithms, so it has been published in Obsearch in the year 2003. And all these algorithms are also exponential time algorithms. I don't want to go into the details of solving how can we apply the algorithm. One can see in the research article. But here the computational complexity of the generalization of modified Dijkstra's algorithm developed by us during the year 2003 is order of n minus 1 into n minus 2 square into n minus 2 factorial whole square. It is also in the worst case analysis. This is the algorithm is exponential algorithm. Okay. And compared to the Caroline-Moon algorithm, this algorithm is better in terms of minimum number of nodes. And another algorithm, it is also developed by us, by a generalization of modified N's algorithm, developed by Dr. Sastry, Dr. Ismail, Mohideen, and Dr. Janagiraman. And this algorithm require order of n minus 2 into n minus 1 factorial square. Again, it is a exponential time algorithm. And the third one, combining these two algorithms, we developed another algorithm, and even it will work with this will we can simply first we can check whether it contains a negative cycle or not. If it negative contains a negative cycle in n minus 2 algorithm, in polynomial time, we can say that it contains a negative cycle. And the time complexity of this algorithm is order of n minus 1 into n minus 2 square into n minus 2 factorial whole square, where n is the number of nodes. This algorithm is also exponential time algorithm. So comparing all these algorithms, which is best? Hence, among the three algorithms, the modified N's algorithm behaves when practically. You can see the word practically. Theoretically, all the three algorithms behave in a worst manner, or theoretically they are bad, but practically the N's algorithm is good. What it means? That means for a problem with less than 20 nodes, the algorithm behaves well. If the number of nodes is more than 50 or 60, the algorithm will not work well. So this is the comparative study. It is not very important. It is only empirical analysis. Now we try to find a polynomial time algorithm to compute a set of Pareto optimal vectors. We try, that is one or two algorithms we have developed. Because of the time constraint, I'm not going into the details of all those things. Just the technique is, that is, we are fast modify the given multi-objective shortest path problem into single objective. Like, how can we modify? You can apply arithmetic mean or geometric mean or harmonic mean or central harmonic mean. Any other mean you can apply. So we tried with many means. The arithmetic mean is always better. So we have modified that. After modification, one can ask whether we will find all set of non-dominated solution. Definitely not. We can only find some subset of set of non-dominated solution. That is, in a number of non. For example, if there are 100 non-dominated solution for a multi-objective shortest path problem, we can find some friendly non-dominated solution. Instead of telling that no solution to the problem, we are able to find some subset of Pareto optimum values for this problem. And the very important thing is the computational complexity is polynomial time computational complexity, that is order of n square into k square into log n plus n power 3 into k. And another algorithm, this algorithm, what here we are doing is, if there are m objective, we will split the problem into m single objective shortest path problem. So we require m times we have to apply repeatedly. So instead of telling that the problem has no solution, we try to give at least some of the Pareto minimum solution. So this is another algorithm. So here the computational complexity is order of n square. Again, it is a polynomial time algorithm. And another interesting topic is genetic algorithm. What is genetic algorithm approach? Genetic algorithm is an algorithm. This is not a mathematical approach. It is not a mathematical method, but using genetic algorithm, we can solve mathematical problem of very difficult problems. If the problem is not at all possible to solve, those mathematical problems can be solved by genetic algorithm. But using genetic algorithm, we cannot find the complete set of Pareto optimum solution or non-dominated solution. Instead, we can find some subset of, or we can say that local Pareto minimum solution. That is, again, a subset of Pareto minimum solution. Interestingly, very important thing is in polynomial time, that is order of n power 3 using genetic algorithm. This is a very important point in the genetic algorithm. In order of n power 3, n is the number of nodes. Order of n power 3, we can find your non-dominated set of or not all the non-dominated solution, set of non-dominated solution. So computational complexity of genetic algorithm to find a set of local Pareto minimum path is order of n power 3. Gentlemen, I am not able to complete all the things, but just I want to throw some light to find say what is or I can say that what is a network problem, what is a single objective, what is a multi objective, what are the different type of algorithms available, what is the time complexity, all those problems I try to explain. If the chuck and tug method is used, I can give more examples. But here it is in the during this pandemic period, we are meeting through virtually. We are meeting anyhow because of the software, because of this modern technology. We are able to interact one another using these tools. So we have to thank our mathematicians, our computer software people, and all those involved, because we are able, even during the pandemic period, we are able to contact and we can do some research. So, in our view, to conclude, if a MOSPP has negative cycle, all the known algorithms available in the literature only indicate the existence of negative cycle, that too after an exponential number of elementary operations. But the algorithm discussed here using non-dominated arithmetic mean vector concept solves the problem with negative cycle, even with negative cycle. Similarly, genetic algorithm may be applied to find a set of local Pareto minimum paths of a MOSPP using the concept of spanning directed tree. There are many more algorithm, there is non-mathematical algorithm called ant colony optimization. Many such algorithms are available. Plenty of literature is available. My dear researchers and young faculty members, I used to tell, Alhamdulillah, by the grace of the Almighty, we are all in a better position compared to the society. The because of the society, because of the poor people's tax paying money, we have settled well. So do some research for the purpose of research, and ultimately your research should help the people, that is downtrodden people. We all, by the grace of the almighty, and if god wishes, alleviate the burning problem of this COVID-19 and the poverty. Wish you all the best. Thank you very much for this opportunity given to me to meet all mathematicians through this webinar. Thank you, Head of the Department of Head in charge, Department of Mathematics, and all the professors involved in this. Thank you for your patient watching. Wish you all the best. Thank you.